Now that we have created the North Pacific grid, we're going to proceed um, to compile the model. So the first thing that I do, I'm going to connect on the master node because that's where you want to compile the model, not on CS. I'm going to go in CD ROMs source and applications. Now for the purpose of this demo, I've already prepared a set of CPP defs for a 3D stratified flow like the North Pacific. So let's open this and let's just go through the various configuration options. So the first thing is we deal with the model physics. In this case we have a three-dimensional flow and it's no longer just barotropic, so we enable this option called Solve 3D. We also want to enable the Coriolis term as we had before, so this option stays there. We're also going to put some viscosity and diffusivity using a Laplacian term, and this is done by using uv underscore vis2 and ts underscore diff2, where the 2 stands for the order of the derivative, in this case a Laplacian second order derivative. We're also going to retain the advection terms, so we enable them by setting uv underscore advection. We're going to use the salinity as a tracer, so we enable it. Because we do have salinity and temperature, the density can be fully computed using temperature and salinity. In this case, I want to compute it using the nonlinear equation of state, nonlin underscore EOS. Now, because this is a more realistic application, we also have to tell the model how to deal with unresolved physics like the one that happens in the mix layer. And so in this case, we enable the LMD underscore mixing, which is a parametrization for vertical mixing in the surface and bottom boundary layer, and this is because we don't fully resolve that. So this is this particular option is implements the KPP vertical mixing, and you can find references. You can find references in the code if you search this option. We then go to the section where we discuss the various numerical schemes that we want to implement. We start by setting that for the temperature and salinity, we're going to use for horizontal advection, H advection, the U3 scheme, which stands for upstream bias scheme, upstream bias implementation of the advection. We're then going to use a spline vertical advection, so here it's TS underscore S, and then V advection stands for spline. And keep in mind that if you are uneasy about what these things are, there's always, for example, your README file where you can find these all these different types of available schemes to you. So this is an example. I just picked some that I typically use myself. Then you can decide what type of horizontal pressure gradient pressure gradient scheme you want. I use this one for now. These two options, mix underscore SUV and mix underscore STS, say that when you mix in the horizontal, you're going to mix along S coordinates, and you can change that. In fact, you can decide to mix, for example, along Z coordinates or along isopycnal surfaces, and these are all options that you will find in the readme.txt file. We are dealing with a curvilinear grid in that you know, the grid doesn't have constant spacing. We also enable masking in that the North Pacific grid has land. We implement this option called Splines, which what it does, it basically, instead of discretizing things in the vertical by just doing, you know, schemes on the native model grid in the vertical, it basically takes vertical profiles and interpolates them using cubic splines, and then after it comes up with the polynomial of the spline, it takes an analytical derivative, and this makes the derivative smoother. So basically you have a polynomial, you take derivatives, you just have some coefficients, and then you re-interpolate back to the model grid. We then have a section of code here that's called if-def LMD mixing, and these are all definitions that are needed for this vertical mixing parametrization scheme. And some of these, again, you can they're kind of self-explanatory, like diurnal SR flux, which means you have a diurnal cycle in the solar flux, shortwave radiation. And others are less intuitive, but really what they're doing, they're enabling pieces of physics that you're not resolving, like R mix and convect. These are instabilities that happen in the mix layer, which are parameterized, and you can check in the README file, for example. If we go again in the README file and we check for LMD underscore R mix, for example, this particular option adds diffusivity due to shear instability, whether the LMD convec option adds convective mixing due to the shear instability. So these are all pieces of physics of the parameterization that you can enable or not. Among which, for example, these LMD SKPP, which turns on or off the surface boundary layer. In this case, we turn it on. And if you want, you can also turn on the bottom boundary layer using the KPP. Now, in our particular case, we only turn up the surface boundary layer because the bottom we don't really care very much in this application. Now, in terms of surface boundary conditions, we have all the surface forcing file, but in addition to that, we're going to specify these two options called Q correction and S correction. And these are options that basically relax the surface salinity and surface temperature climatologies of the model back to observed climatologies. And that's because often there's if you just prescribe a surface flux, for example, you will find that the model will start drifting away because the mix layer of the model is different from the one that is implicit in the surface fluxes that you're using to force the model. And in order to avoid that, we have this S correction term. And in the next exercise, in the next demo, we're going to run a long-term run of the model with these two terms turned on, and we're going to use these terms to compute a corrected surface climatology for heat and fresh water. Now, of course, in this case, we're using prescribed fluxes at the surface. Another alternative, instead of using these correction terms and so forth, is to use bulk flux formulations, which take input parameters like air temperature and humidity and so forth and compute an interactive flux. And these types of bulk parameterization, for example, in temperature, have already built in some kind of nudging towards observed temperatures that come in with these bulk parameters, like the air temperature and so forth. Whether for the salinity, in case of the bulk fluxes, you don't have much of a constraint, so the salinity are kind of unconstrained. But anyway, this is one easy way to get started using these Q correction and S correction terms. In terms of bottom boundary conditions, we're going to use quadratic drag at the bottom, and I suggest you always use the quadratic drag with the realistic application. There's I think some gray literature that explains how this quadratic drag at the bottom could be critical for the model doing the right things, but I don't have time to get into this right now. In terms of surface of bottom salinity and bottom temperature flux, we're just going to use an analytical flux, which is 0. We're not going to have any geothermal heating or so forth. Now, in terms of lateral boundary condition, the North Pacific is bounded in the north, the east, and the west, but it has an open boundary in the south, so we define everything except the southern wall. And then for the southern wall, we implement a set of open boundary conditions. And these include a sponge layer, where the viscosity of the model and diffusivity of the model are enhanced to damp out kind of disturbances that approach the boundary. We are then going to have this so-called south underscore volcans, which says that we're going to try to conserve volume through the open boundary, so that at the end of each integration, the model tries to conserve volume, although you have an open boundary. Now here, these are a whole bunch of set of open boundary condition. So for the free surface F, we're going to use we're going to use a gradient boundary condition, which basically say that the sea surface height gradient at the boundary is 0, meaning that there's no flux across the boundary. For the M2, which is the momentum U bar and V bar, we're going to use a radiation open boundary condition, which again solves a linear wave equation at the boundary, where the advective, where the phase speed of the wave, if you like, is computed through locally by computing the advection velocity at the boundary. We are also going to use the M2 nudging condition, which says that in addition to the radiation at the boundary, the momentum will be nudged to some prescribed value, which comes from the open boundary condition file in this case. The same is true for the 3D momentum, U and V. We have the M3 radiation, M3 nudging, and the same is true for the tracers, where we have T radiation and T nudging. Against the t-nudging, once it's enabled, it uses the values that are stored in the open boundary condition. After this, we're going to also enable the averages, so we write down averages, and we're also going to write the average fluxes, which means that the model is going to store the net surface heat, fresh, and momentum flux that it sees during the integration. And this is important because with these two S correction and Q correction options on, we're going to be able to then use these average fluxes to reconstruct a corrected flux climatology for the model, which we can then use without enabling these options. So this is all for the CPP-def file. I then have, again, as we did before, a compile script and npacific compile. I only have to here tell where I want to store my model, in this case in the bin directory of my examples, and I have to put here the name of the CPP-defs files. And once I have this, I can just run the compilation script, and if there's no errors, you should have a North Pacific model. Now, of course, I forgot to do something before we do this. Since we have this nPacific, we also have to add a couple things, which are the dimensions of the model grid, and we can compute that by just firing up MATLAB. We do grd rnt underscore grid load of nPacific, and now we do grd, and here we are. grd lm and grd mm are the dimensions of the grid in the two directions, and we have 30 layers. So here we're going to go in models, mod param .f, and in the nPacific, which I already have this option here, we have this block of code where I put here the dimensions lm, mm, and n. These are the same dimensions that you set, when you were working with the grid, the GRD. Okay. So with this done, I am going to start compiling this model. And I'm just going to wait for it to finish. So this seems like it proceeded well, and so I do have a successful executable here in this directory, and so I am done with compiling the model. Now, before I end this, I want you to remember that if you go in the main directory of the source code and you do a gggrep of npacific, which is the application that we're doing, you will find all the files where this application has been defined. And if you do that, you will note that there are two additional files here that we've never looked at before. One is called hordsmix_f, and the other one is setnudgecoef.f. These two additional files come into play together with the open boundary condition. In particular, hordsmix.f contains information about the sponge layer. In other words, when you get close to the open boundary, you want to increase the diffusivity and viscosity, and in this file you basically specify how much you want to increase that viscosity and diffusivity. And so, for example, for the North Pacific, all I did is I copied an existing section of code here, which has definition for the southern, northern, western, and etc., all the boundaries, and then I commented out all the other boundaries I don't care about. This is just to have a template. And here you see that in this particular case for the sponge layer, what it has a linear increase in the amount of the viscosity that it's giving at the boundary, in the first in this case 6 points close to the boundary. So basically in the 6 closest point to the open boundary, the viscosity will increase in a linear way by a factor of FAC, okay, all the way to the boundary, and this FAC in this case is 4 times. So basically, if you have a viscosity, say, of 100 meters squared per second, once you reach the boundary, it's going to be 400, and it's going to increase linearly from point number 6 away from the open boundary all the way into the boundary. So this is the way, and you do this for both the momentum and also for the tracers in this case. So this section you can just copy it if you have a different application. You see there's many different applications, US, West, and each application with open boundary has its own definition. And so really all you need to do is to copy an existing section and just put whatever you want, or just use whatever already exists. The other file that is also important is this set nudgecoef.f, and which in this case it's really not used, but if you had, for example, if you wanted to implement a nudging layer, which we didn't do in this particular example, then in this directory, if you go npacific, this is where you define the strength of the nudging, and in this case the nudging coefficient. And here this is a nudging layer, for example, with two timescales of nudging, 1 over 5 days and 1 over 60 days. And again, this nudging layer is in the first 6 points close to the open boundary, and you can see it's just a linear, function. So it goes from nothing in the interior to about 1 over 5 or 1 over 60 days, at the boundary. Sorry, it goes from 1 over 5 to 1 over 60. Anyway, these are just additional options. In this case, we're not using a nudging layer, so we don't really care about this. But this is just to give you some idea of the complexity of things that you could do with this model. Okay, so we've compiled the executable. So if we go in ROM's examples and we go in npacific, we do an ls minus r, and we find that here in the bin directory we have our executable, we have our input files, and we have our MATLAB stuff, and so all we need to do now is to run the model, which is what we're going to do in the next tutorial.